So for this graph, I'm not going to go over like how to find the equation of it, but I'm just going to explain like why it looks like that. So for this one, it's let's see, it has an asymptote of 1. So that means you've got an x on the top and on the bottom. And then you have a discontinuity at 2, so that's an x minus 2 that's on the top and the bottom. Because that, if you set those equal to 0, you're going to get 2, right? So because you get 2, especially if you get a 2 on the bottom, that means that it causes the graph to, in a sense, explode, like it can't do anything there. It jumps over. But when you've got that factor also in the top, like we do here, that's x minus 2, it turns into a hole. If it's like we have here where it's x equals 1, you've got a factor of x minus 1 on the bottom because x minus 1 equals 1. Okay, so x minus equals 1. X minus 1 equals 0, but then you get your x equals 1. Okay, so this is what we call vertical asymptote. Okay. And they don't show it on here, but you can see it as a space that's like this. Little, because that's a vertical asymptote. And then the hole is this one. So if I have the factor on top and bottom, there's going to be a hole occurring at that x value. And another word for this is a removable discontinuity. Removable discontinuity. It has to do with the fact you can look at it as, if I wanted to, I could factor it out of here, couldn't I? There's someone coming in and out, and I'm trying to hold on. Okay. Anyway, so another person coming in. Hold on. Okay, they came in. All right. So back to this. So for the removable discontinuity, you can remove it by factoring it out. That's one reason it's called removable. Another reason is because you can actually define the function by saying that x equals 2, and that would be able to fill in the hole right there. That's essentially what you do when you factor it out. But the loose word for it is a hole. And you can even find the y value for it. We don't need to do that here, but the x value comes from just setting it equal to 0. So I could factor this out. That's the hole in the graph. And we need to have another power of x. I'm just going to do this, and then it's flipped. Okay, so our graph is something like this. I don't know precisely what the equation of it is, but it's something like this. The point I wanted to come across to you is that when you have a single factor on the bottom, you set that equal to 0. That's your vertical asymptote. Okay, so x equals 1. If I plug a 1 in here, I'm going to get division by 0, right? We can't do that. That's illegal move of math. If I plug a 2 in here, that gives me division by 0 also. That's illegal. So, but when I have the x minus 2 also on the top, it doesn't make an entire illegal line like this, a big line. It just makes that single point bad. Okay. So, but that's why those look like that. Does that help with this kind of question? You're welcome. Let me give you one more. Okay, so on this one here, this is destiny, right? You're asking about this one, right? Okay, so which points do you see that we have discontinuities if you're scrolling from left to right? Yep, the 4 is definitely one of those points. What about if we're coming from here? Is there another number that we don't have any values for? That's right. So so that would be your answer there. So we got a vertical asymptote at 3. You can draw a little line like this to kind of, verify it doesn't do anything there. And then you also have the hole at 4. Okay. Okay, so this is, it says graph the function and find values where the function is discontinuous. Okay, so for these are piecewise ones. You don't have one like this, but I'll still go over piecewise just in case. I mean, it's a good skill. This is a college algebra concept. What I would do with this is maybe do another one. I don't know if we can today. We could probably do one again on the review session tomorrow. Let's see how many questions everyone has. But this is going to be lengthy because this is a whole teaching like lesson. All right. So piecewise functions are functions that come in pieces, and to graph each of them, like you don't even know which one of these graphs is here, right? You take each little piece of the domain. So we have one set is for when x is less than 2. And so, I mean, there's this one's x is less than 2, this one as well, and this one. We just need to make sure it's defining it the right way. So when x is less than 2, we have the function -4. That is just a straight horizontal line. It's like y equals -4. If you look, all of these are a horizontal line going through -4. But instead of drawing the entire line, it's restricted to when x is less than 2. How many points define a line? 2, yeah. So you can pick any point. Now, when it's saying less than 2, think about the number line. Any number that's less than 2. Just anyone. You want to put 0, 1, whatever. Just another, right? Okay. When you do that, you're going to draw your graph. I'm going to do it up here. And then you can kind of see the. So we're at -4, 1, 2, 3, 4. And it's the points I have are 0, -4. So here, let me do it in color. And 2, -4. Now, before I draw that one, what I typically do on these, like if we didn't already have a graph there, is I make a note that, see how it doesn't have an equal on there? See how there's no little equal sign? That means that this is open. In other words, you're going to have a hole in the graph. So hole. Unless for some reason it connects, sometimes one of the other pieces connects it. Kind of like what you see here. This looks like these might be a connected one, right? Especially for these problems, you want to draw it out because they're asking where is it continuous and not continuous. So they might have a trick one. Like these are more trick ones where they connect. So, and then when you're drawing your little table to graph it, go ahead and make a note that this particular point right here is going to be a hole in the graph. And then you would go in and draw it. So that point is 2, -4. Let me do this. And this is just kind of an ugly little graph here, isn't it? And that's here. And it's saying less than 2. So it actually points in the direction you're supposed to go, right? But that's going to go like this. So it's just going to go straight through that point. The only ones you have to worry about if there's a hole or not are the boundary points, which are the ones that are given here. Any other like little points like 0, -4, those are just points. They're going to be closed. They're just to help you graph it. They're definitely, okay. All right, that's the first piece. How many pieces do I have? 3. So we're going to do the next one now, the one that's valid from 2 to 5. Oops. Are you okay? Okay. I don't think he knows his mic is on. Okay, so we got x and x plus 1. I'm going to do this one in a different color. And this one's going from 2 to 5. Now, is this what is x plus 1? Is that a straight line? Is it a curve? What is that? You're not sure? Yeah, so it's a straight line. So we have a power of 1 on the x. It's going to be a straight line. If you had a power like an x squared, those look like these. This comes like from here. In business calculus, you went over that a little bit, but you may not have. I mean, not business calculus. You're in business calculus. In business math, like we went over this just now in business math with my students. But if you know, if you didn't spend a lot of time, you might have forgotten. But yeah, so if it has a power of 1, it's just a straight line. So we're going for, that means we only need 2 points. That's why I'm asking that, because then you 2 points define a line. If you have like a power of 2 or 3 or something, you may need more than 2 points to get the shape of the graph. Yeah. And then we want to make a note right here. These both have an equal on them, don't they? Yeah. So does that mean it's included or not included? Yes. So that it's, which is closed, right? So it's closed. And so you can make a little note if you want to of that this is closed. Closed circle. And it's x plus 1. So 2 plus 1, I get 3, don't I? I'm going to do that in black. We'll just write 2 plus 1 here and 5 plus 1. So 2 plus 1, I'm going to get 3. 5 plus 1, I'm going to get 6. So that means on the graph, I've got 2 close points, 2, 3. And let me go up here. 1, 2, 3. And we have one at 5, 6. I'm going to go ahead and just get these little points. Okay. So at 2, 3, and at 5, 6. Okay, so this is going to be like this. So it's filled in. There's no hole right there. Means this one's out, right? And actually, you see how it's open and then closed there? That's this one. It's not this one. But we can go ahead and finish drawing the other part too, just so you can see it. So this last one's also a constant function, like the -4 was. Constant just means it's a flat horizontal. So it's x, and then the y value is 6. I'll just put y here. But it's going to be 6 all the way down, right? And we can pick any x values where x is greater than 5. Now, even though 5 is not included because there's no equal, we still going to put it because it's a boundary point. We just make a little note again that there's it's open or whole, however you want to say it. And then make a little, you know what? Hold on. I'm going to be a little OCD because I think the coloring kind of helps on these problems. Let's do, what color do I want to do? Purple? We'll do purple. Okay, so this one is open. Okay. And that one is here. So when x equals 5, this one is open. There's a hole in the graph then, right? Now the thing is, even though there's a hole, it got filled in over here. It was included on this 5, 6. This is where I'm saying if it's closed, that trumps if there's a hole. Like if one other piece of the thing has it closed, you have to go with that. Okay. And then we can do any point here. I don't know, 7, doesn't matter. But that's going to fill in. And then we have, let's see. It's at 6, right? Let me do one more point here. 5, 6, 7. Purple. That's not very nice. And then it just goes like that. But yeah, so even though that says hole here, this, it trumps that. Okay. So closed since one of them is closed. As long as one of them says it's closed, it's going to be closed, okay? Since one piece says closed. And I'm just putting this because I'm going to post this with a video again, like the last one I did. I'm going to post the PowerPoint, so if those that didn't get to come can look at it. Okay. And I might post the PowerPoint earlier. I don't know, because last time it took me a long time to edit the test or the session because it's an hour long. It takes a long time to load and edit it. Okay. All right. So yeah, that's just a quick rundown of the piecewise ones. And I mean, you can do this on the calculator. I don't know if you want to see that because y'all can use the graphing one. You want to see that? Okay. All right. Not this one. That one doesn't work. I think we had -4, right? And that was when, so we put the portion of the graph we have, and then what we do is we go second math, and that gets you these things. And it was when x is less than, right? So pick the less than. Oh, I forgot my x. X is here. And then less than. And it was, I believe, 2, wasn't it? Okay. So that's one piece. And you're going to put a plus. The next equation was x plus 1. I'm going to put a parentheses because there's more than one thing. The -4 I didn't have to because there's just one thing. And it was in the front. But x plus 1, and then the restriction was there that, I think it was that 2, if we go to math, less than or equal to x. And you have to do it in separation like this one. And then it had x less than or equal to, I think it was 3, wasn't it? I'll double check it before I hit enter. But that's another piece. And then you go to the second. Okay, I'll show you again in a second. Let me put the thing in there first. Okay, so the next one was, I believe it was 6, right? And that's when x is greater than, let me actually look. I forgot what it said. It was 6 when x is greater than 5. Oh, and that's a 5. That's not a 3. Let me change that. Sorry, let's see. So this is a 5. And it's going to be 6 when x is, and then here's where you go. You go second math. And you can get these. Did you see that? Okay. So then after that, you just hit graph. See? It doesn't show you the hole, but if you don't know where the hole is, like at 2 right there, like, because you're looking at the picture of it, right? And you don't know which one has the hole. On the calculator, what you're going to do is you're going to hit trace and you're going to hit 2. And notice that it's up there. That means there's a value there. There's no value right here. Okay. And then that's it. Yeah. So this is the only point where we have a discontinuity then. We didn't really answer the question yet, right? But this is the only place where there's it's discontinuous, because if you trace your pencil along, even though there's a value right here, there is a function value, it's still discontinuous because you're having to jump up and go here, aren't you? Yep. But if and you can see the holes filled in on this one. But if you're not sure, hit trace. That was it. 1, 2, 3, 4, 5. Yeah. So we actually have a 5, 6 a value. So that's it's continuous right there because there is a value, but not here. There's a value down here, but then it's nothing. I'm sorry, it's up here, but not down here. That's a jump discontinuity. And that was what was that at? That was at 2. So the graph was, where was the value at? Was it down? I think it was this one, wasn't it? Is that what we picked? Oh no, we picked the second one because there's a value at 5, 6, and there's a 2, 3. Okay, so the second one is the one. And then it says select the value of x for the function is discontinuous. It's just going to be right here at 2. And that's it. Okay, so we want to find f prime. What we're going to do is we use the power rule. This is the one I went over last class if you were here. So, but I'm going to write it down again. So if I have a x to the n, and I want to find the derivative of it, this is the notation we do for the derivative. Okay. If I want to find the derivative of this, basically I take whatever my power is and I multiply it in front. So it's going to be n times a. And then it's times x raised to the, what I do is I take 1 away from the power. So n minus 1, whatever that, so the power is 3. 3 minus 1 is going to be 2, right? And I put the 3 in front. So we're going to do that here for each piece. So for this, it's going to be, this goes to the front. So I've got, I'm just going to put the negative in the front, but it's 3 over 2 times 12, okay? And then we're going to do x to the 3 halves minus 1. This is why I had y'all do the fraction practice in case you have trouble with this part. Okay, plus, and then the 1.3 comes to the front. We're going to do that one as well. So 1.3 times 5 to the times x to the 1.3 minus 1. So we do the subtraction. And then when it's a single number like this, I mean the variable, it's just the number in front. So there's a 1 in front of the x that's understood, so it's just going to be plus 1. Okay. If you need to see why, just look. I think I explained this last time, but please don't sit there and write this out each time. Just know that it's the coefficient in front, whatever that number is. So 1 times x to the 1 minus 1. Okay. All right. Okay. Then here we've got negative 3 halves times 12. So that's going to be the cancel. This is 6. Negative 3 times 6 is negative 18. And then we got x. 3 halves minus 1. I can write that 1 as 2 halves. Okay, that's the easiest way to do the fractions. You just look to see the bottom of this one and make that over that. Very good. And then 1.3 times 5, it's going to be 5, 6.5. And then we have x to the 1.3 minus 1 is 0.3. Plus, and then this 1 times x is just x to the 0. Anything to the 0 is 1. Any number that I have to the 0 is always going to be 1. Okay? Okay. So then here I've got, let's see, negative 18, x to the, just like you said, it's 1/2, right? Okay. Plus 6.5, x to the 0.3. And then, like I said, anything to the 0 is 1, so that just becomes 1. That's why I told you it's always going to be whatever the number is in front. If there was a 2x, it would be 2. Now, we can write this way. It's probably going to take it like that, but I need you to understand that x to the 1/2 is the same thing as square root of x. You may have some problems where you have to convert back and forth. So I think it'll take it like this, though. We can look and see. Let me take a picture of it so I don't have to toggle back and forth. So negative 18 x to the 1/2 plus 6.5 x to the 0.3 plus 1. Okay. So it says here, for the given function, find the slope of the tangent line to the graph at the point. And so the slope of the tangent line, that's going to be m. It's going to be the derivative at that point. So it's going to be f, or that's actually h. The function's called h. It'll be h prime, the derivative, okay, of 7. So the slope at that point is going to, because it's at this point 7. To be able to do this, first of all, you need to write h of x as a power. This is why I put those exponent things there for you. If I have an x in the denominator, we need to move it up. When I do that, it's going to become 8x, but it changes. Right now, since it's a power of 1, it's going to be negative 1. Okay? And then that's actually h. Okay, so we're going to do h prime now. H prime of x is the derivative, so we do that same power rule. So negative 1 times 8, I'm going to go ahead and write it out for right now, times x to the negative 1 minus 1. I have to subtract, right? Power rule. So ax to the n derivative. Just going to write it again over here. That's n times a times x to the n minus 1. Okay. All right. And then that's going to give me negative 8. X to the negative 1 minus 1 is negative 2. Now we're going to do some more math things. This is again understood to be over 1. I don't want to have a negative exponent in my final answer. I'm going to move it back down now. So we have the negative 8 on top because that doesn't have that negative power. It stays there. But the x to the negative 2, I move it down, and guess what happens to the power? What does it become? Square. So it becomes a positive 2. And so now that we have the derivative equation, that'll give us the slope at any point on the line, but we want the specific point, that tangent point at 7. So we're going to do it in here. Let me actually do it in a different color. So we're looking particularly at 7, or specifically at 7. So it's going to be 7 squared. Okay, so that's going to be negative 8 over 49. So that's part A. That's the slope of the tangent line. And then the equation of the tangent line, we have this formula, y minus y1 equals m times x minus x1. Now, we already have the slope. That's m. We need to find the y values. The only thing missing, we have the x value of 7. Y value is super easy. It's just going to be h of 7. I'm going to go ahead and plug that 7 in there. So it's the function value at 7. And that's going to be 8 over 7, isn't it? Okay. So the equation is going to be y minus, and we could put y1 here if we want to. It's just the point, and this is x1. Y minus 8 over 7 equals m is negative 8 over 49 times x minus 7. That's it. That's the equation. Okay, the slope we said was negative 8 over 49. Okay. And then the equation, let's see if they let us do it. Y minus, they may make us do the other way, but we'll see. It's easy to move it over, but equals, and then we've got negative 8 over 49, and you can put the negative anywhere, but I'm going to put it just outside. 49 times x minus 7